All right, so today we're going to talk about domain and range, and we're going to spend a little bit of time describing what it is, what it means, what it stands for, what it's used for, and all that kind of goodness, okay? So domain and range. Domain is going to be your independent variable. It's going to be your right and left motion when we're looking at this. Like you might even put underneath domain the arrows pointing to the left and to the right. It is your x-axis. It is your left and right motion. On an equation like y equals mx plus b, your x is going to be your domain. It's your independent variable. It's the input of what actually goes in and solves the equation. Your range is going to be your independent variable, and it goes up and down the graph. It describes the upper and lower limits of what this graph is. I say limits because not every graph goes on forever and ever and ever. Some graphs have a specific limit that they cannot go below. You haven't had a chance to see it yet, but in algebra, you'll have a graph and it will have a curve on it that goes like this. In that case, the graph doesn't go below that line right there. This would be a lower limit that we would want to use and be able to describe on it, okay? I have these shaded in different colors so we can see what each of these represents. I make a table out of it where I alternate left and right, and I use the phrase or the name Dr. Idiot in order for us to remember what's going on. Doctor, DR, domain range. I start on the left side with domain, I go to the right side with range. From there, I look at my independent and my dependent, ID from idiot, okay? Input and output is important as well because it describes going into the equation on X and the output being when we solve the equation with Y. All right, T at the end just stands for the T at the end of input and output. Okay, so we do need to know what each of these are because it can ask you for it in different ways when it comes to the STAR questions. Okay, so in order for us to better understand it, let's talk about it when it comes to a graph. Now on this graph right here, it says that Mr. Ring goes shopping for cans of dog food. Each can costs $1.50, and Mr. Ring has $10 in his wallet that he can spend. Graph the number of cans that Mr. Ring can buy and how much he will spend on the graph below. Label each axis with what it represents. Also write the maximum and minimum that you can spend and the maximum and minimum of cans that you can buy. Okay? So when I look at this, I see a couple of things. When I think about maximum amount of money that you can spend, that's interesting. A lot of people might jump to the conclusion that, oh, Mr. Ring has $10, so he can spend all $10 on this. And they kind of go with that as the answer. But the thing is that's not quite correct. That would not be the answer I would want to put here. If we do a little bit of math and we do $10 divided by 150, it doesn't divide out equally. Something that I might want to do on here is I might want to start thinking about creating a set of table of values or something like that that we can then graph on this coordinate plane. Okay, so let's start doing that. Now, let's start with the minimum number of cans of dog food, okay? Minimum. What do you think the minimum number of cans that I can buy is? Well, if you go to the store and the store does not have any dog food, then I wouldn't be able to buy any cans. If that is the case, then 0 cans of dog food leads to $0. Which means that is the the minimum number of cans that I can buy and the minimum amount I can spend. You know, aside from the time and the effort it took to get to the store, but that's not part of this problem here. Let's talk then about our next step up. Buying 1 can for $1.50, 2 cans for $3, 3 cans is going to be $4.50. 4 cans is going to be $6. 5 cans is going to be $7.50. 6 cans is going to be $9. 7 cans is going to be $10.50, which is going to break the bank, and it is going to be too much. I cannot buy that many cans. 7 cans is off limits, but I can spend the $9 and buy 6 cans. And so that's what I'm going to put as my maximum. 9 cans, excuse me, not 9 cans, excuse me, 6 cans and $9 is going to be what I can spend. Now, when I go to graph it, 0, 0, 1 and $1.50, 2, $3, 3 and $4.50, 4 and 6, 5 and $7.50, 6 and 9. That's going to be the dots that I can draw on here. Notice they're not perfect, but they are close enough to be able to convey the meaning of what this graph means. Now, the next thing I might think I want to do is to connect the line that connects these dots, like draw it in there. But that is the last thing that I want to do. Drawing a line indicates that this is a continuous change, as in I can have partial values, like buy half a can of dog food, and that's not okay. You know, you don't go to the store and buy half a can of dog food. You go to the store and you buy a whole can. You don't go to the store and buy half a shirts. I know, crop tops, but no, you buy a shirt and you get the whole shirt for the full price. Or if you go to the store to get like an ice cream cone, you're not going to buy half of an ice cream cone. You would need to buy a whole one. That's going to be a 1-to-1 kind of proportion, where when you buy one thing, you're spending a certain amount and you can't do partial values. Now, if you wanted to have a continuous graph that would be connected like a line, you could buy like gas, like filling up your car. At that point, you could buy a partial gallon of gas and not spend the full price for the full gallon of gas. Same when you're looking at going to like a Orange Leaf, where you get the yogurt. The scale works in increments where you can buy, a quarter pound of froyo and spend just what it is for that, okay? In this case, this is going to be what the graph is. What I want you to get in the habit of, though, is I want you to get in the habit of labeling the range and the domain on these graphs. The range going up and down, and the domain going left and right. Always range up and down, domain left and right. Also, we want to label what these sides represent, where the range represents how much money we could potentially spend, and the domain talks about the number of cans, in this case, of what this situation allows us to have, okay? This is what I want to see on each of the examples going forward, as well as on your worksheets. Now, on number 2, it says, These Tees sells shirts for $8 each. Hey, we already know about these shirts. You're not going to be able to buy half of one. The business currently has orders for 3, 8, 5, and 6 shirts. Label the X and Y axis. Label each of the axis, the domain and range. Write what part of the problem the X and the Y represent. Graph each point. You can make up the divisions on the chart as you need to. Then answer the maximum and minimum numbers to the side of the graph. Now, if I look really carefully at this, if I look at the minimum and the maximum, I'm actually looking for the orders here, okay? I'm gonna say, okay, I have orders for 3, 8, 5, and 6. And if I look super duper closely to that, I notice that it's 3 is the lowest and 8 is the biggest. And if I happen to put 8 over here, I can't even do this in a small enough way to be able to get seen, excuse me. If I put 8 over here and I go backwards, 6, 4, 2, and 0, we would be able to use this to represent the number of shirts. This is also gonna, again, be the domain. I want to have those labeled. The next thing I want to talk about is the range, okay? The range of values that we could get as an output for this kind of depends on what goes in, okay? In this case, again, the range talks about money. Anytime you're talking about money, the range is going to be that. It is going to always be on the y-axis there. And if I think really carefully about it, I could just count by eights going up, 8, 16, 24, and 32 as I start tracking this, okay? Now, when I look at the maximum number of shirts, if I look at the orders, I do know that the biggest order I have here is 8. And if I think about it, no, I can't do it by 8, 16, 24, and 32. I apologize, guys, because if you think really carefully about it, if it's 8 shirts, how much are we going to spend? At $8 each. Well, 8 times 8 is 64. So I don't have enough space up here. So I need to be careful about that. As a reminder to y'all, I'm gonna leave the error in here so you can see, it might be better to go ahead and get my table of values going before I start doing that. So if that puts 64 as the biggest, I'm gonna wanna kind of divide that by 4 going down since there are 4 lines, and 64 divided by 4 is going to be, what is that, 16 each? 16, okay. So 64 take away 16 is going to be 48. 48 take away 16 is going to be 32. And then I have 16 here. So we're going to want to be kind of careful about how we measure these, but it'll be fine. Oh, by the way, we just calculated what the maximum order was, which was $64. And I can plot 864 by putting a dot up there. The minimum number of shirts. What is the smallest number of shirts that are ordered? In that case, it is the 3, not the 0, because I do have an order for 3 up here, okay? For 3 shirts, my money is going to be $24. Now, I'm gonna go in between 2 and 4, and I'm going to go about here. I'm gonna go up to where it has a $24, and that's between 16 and 32. I'm gonna put a dot here. That's gonna be that order. And the minimum order for that is my 24 that I just got. From there, I just need to do the same thing for the 5 times 8, which is 40. 4 between that is 5. 40 is gonna be here. And then for 6 shirts, 6 times 8 is 48, which is gonna go here. And again, as much as I want to connect these dots with a line, I'm not going to because they're not continuous. They're not connected to each other. This is again, I'm gonna say the word, discrete graph because these dots are not connected. They are separate from each other. I have one more example I'm going to go over with y'all, and I'm going to ask you questions along the way on this, okay? So Mr. Johnson is handing out flyers for his new business. He starts the day with 300 flyers and hands them out all at a rate of 75 flyers per hour. Label the X and the Y axis. Label each, the domain and the range. Label the X and Y axis, and also graph each point. You can make up the divisions to fit the chart as you need to. Then answer the minimum and maximum numbers on the side of the graph. Okay, so when I look at this, again, I have 4 lines up from 0 that I'm going to be able to use. And so I'm probably going to want to take 300 and divide it by 4, which, by the way, it is possible to divide by 4, okay? If I take 300 and divide it by 4, excuse me, 7, that's 28. Take away, that gives me 20, because I'm bringing down that 0. 5. So if I take 300 and I divide it by 4, I get 75. So my increments are in 75. So I go, okay, if it's 75, I have 0, because it is 0. I can hand out 0 flyers. 75, 150, 225, and 300. By the way, if I look at this, if I know that he's going to hand out all 300 like that, I can solve for this. He could hand out all 300. And we can start looking at how many flyers he has and go from each place, each hour that passes, okay? So if he starts at 0 hours, he has 300. I can also write an equation to represent this, and I'm going to go ahead and ask you to do that as well. Let's start by writing an equation of y equals something. It's going to be a y equals mx plus b looking thing, but I'm going to use the words from this, the 300 and the 75, and let's see what you're able to come up with. Your goal is to write an equation in the form of y equals mx plus b. The video is going to solve. Type it in, and let's see what you come up with. All right, so what I got here is it's going to be y equals negative 75x plus 300. The negative 75 is because he loses 75 flyers per hour as he hands them out. The plus 300 indicates the positive 300 that he starts with. So if I look at for 1 hour that he is solving, or that he is sending out, negative 75 times 1 is negative 75. 300 take away 75 is 225. If he's going for 2 hours, 2 times negative 75 is 150, a negative. Subtract that from 300, and I get 150. That's 2 and 150. What about 3? 3 times 75 is going to be 225. And when I take that away from 300, I'm at 75. So that's 3 to 75 being left. And then just like before, when we look at the 4, our 4 times 75 is 300. When I take that away, it's gone. So that means I know that I'm going from 0 to 4 hours. And, to track that, I'm going to, again, go 1. I'm going to go with a 2, a 3, and a 4. All right. And then I can go ahead and graph these on here as well. 0 flyers at 4. I have 75 at 3 hours. I have 150 at 2 hours. I have the 225 left with 1 hour that he's been handing them out. And again, I started at 0 hours with 300 of these. Now, in this case, if I think really hard about it, he could be looked at 2.5 hours, 3.5 hours, 4 hours. You're going to have a bunch of little dots that are going to go in between here. And all these little dots that are in between are going to represent how much time he has passed as he's passing out these flyers. But the thing is, each of these dots that is in between is still not connected, because even though he might have passed out 163 flyers, that is still an exact number. He's not going to have half of a flyer left when he's done passing something out. So this is still going to be a discrete graph, not a continuous one that is connected. Okay? Once again, the bottom talks about the hours. The left side talks about the flyers that he has. The maximum number of flyers he can ever have is 300. The minimum is 0 because he does have the potential to have them all passed out. The maximum amount of time he can spend passing out flyers at this rate is 4 hours. The minimum amount of time is 0 because if he doesn't pass out any flyers and no time has passed, it is still a measurable thing. And that's what we can talk about on this graph. Now, the reason we talk about this domain and range like that is because if you think really closely about this situation, Mr. Johnson is never going to have negative flyers. He has a set floor of 0. There's no possible way that he could end up with more than 300 flyers as well. That is the most he starts with. He is going to never have any more than that. Nobody's going to walk by and say, "Oh, Mr. Johnson, I have more flowers for you, or flyers for you." It doesn't happen. So it has that. Also, you're not going to have less than 0 hours spent passing out flyers. There's no negative time in this situation, so we're not going to be able to go any further outside of this. Additionally, assuming that Mr. Johnson stays at the same rate, and in this case, he is going to stay at the same rate. There's no ifs, ands, or buts about it. He can only spend a maximum of 4 hours passing out flyers. He can be anywhere in the middle of this. All of this stuff here, he could be anywhere inside this time frame here. That's what domain and range does, is it gives you the maximum and minimum values of a situation on this graph. And each of these situations that we were looking at are able to be investigated the same way. Now, there are times that it can go off to infinity, and we are going to talk about that a little bit more in the future. But for now, for today, you're not going to have to think about that. You're only going to have to think about the disconnected dots that are on the graph, or if they're connected, that they're connected. And being able to label these sides as the domain. You do need to make sure that you have the domain and the range taken care of, as well as labeling each of these axes with the fact that, okay, this represented flyers, this represent the number of hours that were spent, and that it's the domain and that it's the range. If you do have any questions, don't be afraid to ask. I do have every bit of faith that you will be able to complete this though, okay? Thank you guys.